So, great. Okay, so today I want to remind us what we talked about last time. So just the setup was, recall, if we're given some Hermitian that is a self-adjoint matrix, so some self-adjoint matrix A, so we call it self-adjoint just means its adjoint is equal to itself. We sometimes call this Hermitian, right? And this can be in either the setting of the complex numbers or the real numbers. So maybe what I'll do is I'll just say over F, and then just remind you really fast that F can denote either the real numbers or the complex numbers. So you can play the whole story today with the real numbers in mind or with the complex numbers in mind. So given such a self-adjoint matrix, last time we showed that the following are equivalent. The first is that we could say that A is positive semi-definite. And then alternatively we could say positive definite, but let's just focus today on semi-definite. Recall this means that if you take any vector v, v conjugate transpose AV will be non-negative. Non-negative for whatever v you want in Fn, be it Cn or Rn. But that condition we showed last time is equivalent to saying that the eigenvalues of A are non-negative. If we strengthen the word here from positive semi-definite to positive definite, that is where this product comes out to be strictly positive for a non-zero v, then we would strengthen this to be positive eigenvalues, right? So there's an analogous statement. If you just strengthen this to greater than, then your eigenvalues become strictly greater than 0 as well. But for now, let's just stay in this setting. Furthermore, since your matrix is self-adjoint, it is normal, so we can apply our spectral theorem, and we get that you can write A as some unitary matrix U times a diagonal matrix D times U conjugate transpose. Since it's self-adjoint, all the entries in D are going to be real, the eigenvalues, and we've just said that the eigenvalues are non-negative, so this is equivalent to saying you can write A this way, where the entries of your D are non-negative. Zeros everywhere, but along the diagonal, non-negative. You may have some zeros there, you may have some positive entries. And then finally, the one I'm really interested in that we're going to spend most of our time today talking about was a last condition, which said that we can write A as B conjugate transpose B for some matrix B. So once again, if you're working over the complex numbers, those have complex entries. If you're over the real numbers, have real entries. So it's whatever field you're working over. And so this is the statement I want us to focus on. This is the statement I want us to think about today. Because the question I have for you is this B unique? By the way, this is sometimes referred to as your positive semi-definite decomposition. A theme of this half of the course is looking at how do you decompose a matrix into other products of matrices, and here's a particularly important one. If you have a positive semi-definite matrix, you can decompose it as a product of a matrix with its adjoint, with its conjugate transpose. So, is B unique? Asked another way, might we ever have B conjugate transpose B coming out to be the same thing as C conjugate transpose C. Yeah? What? How?
Two different unitary matrices.
Okay, so if these were both unitary, they would just both come out to be identity. So that's certainly true. But actually, there's another trick you can do. So B isn't necessarily unitary. I don't have any restrictions on B, right? But I do have that if I had such a B, if I was able to find such a B, I claim I could construct C as just some unitary matrix times B. If I do that, I claim that will then give you that the product between B conjugate transpose B is the same as C conjugate transpose C. And so let's think about this really fast. What is C conjugate transpose C? Well, that's UB conjugate transpose times UB. But then that's just going to come out to be B conjugate transpose U conjugate transpose UB. And since U is unitary, this is simply going to become identity in the center. So we have that C conjugate transpose C is equivalent to B conjugate transpose B. They're equal, right? That is, B is not unique. You can multiply B by some unitary matrix, and you have something else that decomposes your matrix A. So this result here is often referred to, we're going to have more to it, but it's called the unitary freedom of a positive semi-definite decomposition. So that's a mouthful, right? But all it's saying is once you have some decomposition of a positive semi-definite matrix, you're free to choose your B up to multiplying by some unitary matrix. Yeah? Okay. Well, it turns out we can say a lot more. Once you know these are equivalent, then I claim, well, let's think about what happens if you do some matrix, well, I'll just write the claim and then you'll tell me why it's true. I claim that BV dotted with BW should be equal to CV dotted with CW for any V and W in whatever your vector space Fn is. So like, well, why is that true? Well, we just unpack the definition. Like, what is BV dotted with BW? This guy on the left-hand side is just the conjugate transpose of the first times the second. So this guy on the left is just V conjugate transpose B conjugate transpose BW, right? Dot product is simply the conjugate transpose of the one times the second. If you're working over the complex numbers, if you're working over the real numbers, just the transpose. But then you can just say, well, and we just said above that B star B is C star C, so that's the same as just V star C star C W, which is the guy on the right. So that immediately follows from the one above it. And then once you know that's true, if you set your V and your W to be equal to each other, you just get BV dot itself, which is just the magnitude of BV squared, comes out to be the magnitude of CV squared. But since magnitude by definition is non-negative, you get the magnitude of BV is equal to the magnitude of CV. So this is done by just setting your V equal to W. Set your V equal to your W. And again, that's for all V. Okay. I mean, this shouldn't be like super shocking because we said that the difference between B and V is just some unitary matrix. And unitary matrices don't change length, right? So I'm just kind of unpacking some of the consequences. Okay, well, I've shown you very quickly all of these implications. It turns out it's also true that you can loop this. And so once you've done this, you then get a series of statements that are equivalent. The following are equivalent. But this last step, as is often the case, takes a lot of work. And so I'm not going to spend time on this. I want to get to the big story, but you can prove this, and it's in the book if you're interested in going through and seeing the details of that proof. Hopefully it's believable though. And so now we have a series of conditions, but what they're merely telling us is that if you have some positive semi-definite matrix, you can decompose it. That decomposition is unique up to multiplying by a unitary matrix. So maybe as a very crude analogy, when you take if you have x squared equals 9, there's a solution to that, 3, that's unique up to sign, right? It's there's two solutions, it's plus or minus 1. It's the same thing. If you want to break this down, it's a unique solution up to your choice of sign, right? Where your unitary matrix is kind of like playing the role of that plus or minus 1. Okay, I'm going to develop that analogy a whole lot more throughout the rest of this lecture, particularly about the last 10 minutes. We're going to see that's such a very powerful analogy I'm hinting at. But maybe that's at least enough to get the spirit of this. Okay. Well, actually, let me pick up the analogy some more right now. Theorem. I kind of hinted at, you can kind of think about A as being like B squared, but it's not exactly B squared. It's B conjugate transpose times B, right? So it's not exactly B squared. But what I want to say is you can write A as something squared. So if you're given some positive semi-definite matrix, A, what I want to say is there exists a unique positive semi-definite matrix P such that A is actually equal to P squared. So it's not just writing A as something conjugate transpose times itself. A is actually equal to P squared. And this P is called the principal square root. The principal square root of the matrix. It's unique. Okay. So I'm going to prove this by just constructing it. Proof. Why can we do this? So we want to prove existence first. In a second, we'll have to come back and show it actually is unique. But for existence, it's quite easy. So A is a positive semi-definite matrix. So in particular, that means A is self-adjoint. To be positive semi-definite is a subclass of self-adjoint matrices. And so therefore, since it's self-adjoint, we can apply the spectral theorem. And so we can write A as some decomposition of a unitary matrix times a diagonal matrix times U conjugate transpose. So we may write A as U conjugate transpose. And so now help me out. If that's what A is, what should I define my P to be? What was that? Yeah, U, d to the 1/2 power, or square root of d. Just raise all the diagonal entries to the 1/2 times U conjugate transpose. Why can I take the square root of d? Well, since A is positive semi-definite, I know that my eigenvalues are non-negative, so the entries along d are non-negative values, so this is well defined, right? So I can just define P this way. I can't do this in general, but I can do it if my eigenvalues are non-negative. so I can do it for these positive semi-definite matrices. And so then let's just check. What is p squared? Well, p squared is going to be u root d u conjugate transpose times u root d u conjugate transpose. In the center, we just have identity, right? This just comes out to be identity. And so then you just get root d times root d, so that recovers your matrix D. And so you get u d u conjugate transpose, which is A, exactly like I wanted. Although let me note something really quick. Here, this D had non-negative values, non-negative eigenvalues. When I take the square root, it's still non-negative. So what do you call a matrix that can be decomposed in such a way that you have a diagonal matrix in the middle with non-negative eigenvalues? Well, P is positive semi-definite. So I'll also just note, and P is positive semi-definite. Hence, in particular, P is self-adjoint. So P conjugate transpose is equal to P. Thus, as well as saying that P squared equals A, P squared is also the same thing as just P conjugate transpose P. So whenever we can decompose A into some positive semi-definite matrix times itself, well, then that's going to be the same as writing A as just times P squared. P conjugate P is the same as P squared, right? But I'm saying there's only one guy. There's only so this is the same thing as P conjugate transpose P, and there are lots of B conjugate transpose B that give you A, but only one of them is actually positive semi-definite. Only one of them is actually the same as P squared, right? Okay. So now I have to show uniqueness. So I'm trying to show uniqueness now. So why can't I write A as some other thing squared? As some like Q squared, for example. Well, suppose A is equal to some Q squared. And we've already said A is P squared. What do we want to show? How do we show uniqueness? Like, what do we want to prove? That will show us that your P is unique. Right, the goal of this proof should be, I want to show WTS, want to show that Q equals P. So let's like keep that goal in front of us, right? Like maybe I'll even like underline it, because we're going to come back, just level a box. This is our goal in this proof. I'm going to be doing some manipulations with Q and with P, and we might get lost, but we're going to come back and ground ourselves in this reminder that we're really just trying to show that if Q squared equals P squared, and these are both positive semi-definite matrices, then actually your P is equal to your Q. That's where we're headed. Okay. So here we go. So where this is your P and your Q are both positive semi-definite. Okay, I recognize a lot of acronyms on the board right now. Right? Positive semi-definite. Want to show, that's just 2. Okay, we'll be okay. So, how are we going to show these equal? Well, we already know what P is. We know that P, we defined it to be this way, is U root D U conjugate transpose. So P squared is just U D U conjugate transpose. And, Let me make sure I do this right. And I don't know what Q is, but if Q is positive semi-definite, then by my theorem, if I have a positive semi-definite matrix, I can decompose it, spectral theorem, where the values of D will be non-negative. So I can write Q as, I don't know, some unitary matrix V times some diagonal matrix. Okay, I need another letter. I've already used D. What's another letter for diagonal matrix?
Delta.
Delta, a capital delta? Like that? What kind of universe are we living in? Okay, yeah. That just looks bizarre, but oh, I don't know if I can do that. Sure, that's going to be our diagonal matrix. Wow. I don't like that at all. Can we not do that? I'll just call it E. Okay, E is not an elementary matrix. It's just another diagonal matrix. So let me just clarify here. My V is some unitary matrix. And my E is some diagonal with non-negative entries. So I have Q squared V E squared V conjugate transpose is equal to P squared. Is equal to U D U conjugate transpose. That's what I have. What do I want to show? I want to show Q equals P. So let me just rewrite that in terms of these decompositions. Q is V E V conjugate transpose. P is U D U conjugate transpose. This is what I want to show. Right, it's the same statement as above. I've just translated into decompositions using the spectral theorem. Not D, not D. P is the square root of D. That's what I want to show. I know these are equal, and I want to move to these being equal. But let's just think for a second. When you have a decomposition like this, both of these equal the same thing. These are both just A, right? These are both A. Maybe I should have put an A in the middle. This is A, this is A. These are both A. And when you decompose it, your diagonal matrix is just the eigenvalues of A. So both of these are just the eigenvalues of A. Now, you might worry a little bit that, well, maybe the eigenvalues on this side are in different order than the eigenvalues on this side. True. But up to rearranging those eigenvalues, up to rearranging, we can say that my E squared is equal to my D. The same diagonal entries, right? And since A is positive semi-definite, these are non-negative eigenvalues. Non-negative eigenvalues. So I can take the square root of both sides, and so I get that my E is my square root of D. Now we're not done yet. Right, I've shown that my E is the square root of D, but that doesn't deliver that this whole thing is the same thing as this. My U and my V would be very different matrices. So I still have some argument to do. I've shown that these matrices in the center are the same, but now I need to show, well, I have this U and this V, I need to show they're the same. And so how are we going to do that? Well, looking at this, can we simplify this at all? And one way we might try and simplify it is we could move, say, this U over on the left as U conjugate transpose, and you can move this V over to the right as from V conjugate transpose to V. That's saying what we really want to show here is that we want to show that U conjugate transpose V times E is the same thing as root D times U conjugate transpose V. U conjugate transpose V. That's what we want to show. And so if I let W equal that U conjugate transpose V, note it's still unitary, it's a product of two unitary matrices. Then what I'm trying to show is I'm trying to show that W times E is equal to the square root of D times W. So that's what I really want to show. But I already know that my E and the square root of D are equal to each other. So last time, let me just state the goal. We have the E and D are equal. Therefore, we want to show that W times the square root of D is equal to the square root of D times W. That's what we need to show. Okay, just trying to be clear that we know what the goal is, like where we're headed, so that when we're done, we can be convinced that we're done. Okay, what do we have so far? Well, let me pop back up. We have this. And just like before, I can construct W by moving the U over as U conjugate transpose, and moving the V over, V conjugate transpose over as V. So from this statement, we have, if I move this U over, U conjugate transpose times V times E squared, but E squared is D, so times D is equal to, over here I have D, and I move the V conjugate transpose over as V, U conjugate transpose V. So I have already WD equals DW. And so I want to go from this, that WD equals DW, to conclude that W root D is equal to root D times W. Right, that's the step we need to make. If we can move from here to here, we'll be done. So let me just pause for a second. Any questions so far on the proof or what we're trying to show, or any steps?
These want to show statements are all equivalent?
Yeah, these are all equivalent. Well, once I knew that E is root D, I was able to move from this one to this one. Yes?
So once we have that, so because the E squared is equal to D up to the rearranging of the eigenvalues, wouldn't we have to include like a unitary matrix being multiplied by one of them that swaps the positions of the eigenvalues to actually say that they're equal?
It swaps the position.
That swaps them along the diagonal. Because
we just want to show that the Q is equal to P. And so rearranging the columns of E with the corresponding columns of V and V won't change Q.
okay.
Right? That rearrangement leaves Q constant.
Right.
Good. Okay. So here's what we have. So let's think about what we actually know. W, I don't know what W is. But W is some matrix, you know, W11 through W1n down through Wn1 through Wnn. And on the left-hand side, we're multiplying it by some diagonal matrix, lambda 1 down through lambda n. And if we think about what this means, and then zeros everywhere else, we're going to be doing row times column, right? So the first entry in the top left would be like W11 lambda 1. And then you do row times the next column, and the second guy gets saved. It's like W12 times lambda 2. And you keep going, so that by the time you get to the top right entry, it's the top times here, so it's W1n times lambda n. Right, that's the pattern. And it continues, but maybe I'll just express this by saying, notice it's like W1I times lambda I. And then the next row would be W21 times lambda 1, W22 times lambda 2, and so forth, down to the bottom, Wn1 times lambda 1, Wn2 times lambda 2, and so forth. That whole pattern can be expressed by just saying that it's a matrix where the elements of the matrix of the form Wij times lambda j over all I and j, right? Where your I and your j are running from like 1 to n. Right, so it's that whole matrix, all those values. The ith jth element looks like this. Okay, maybe this is cumbersome to write this. But you have n by n matrix with ith jth element looks like this. How about on the right-hand side? Well, on the right-hand side, the story's flipped. So first you have the d, lambda 1, and then you have, through lambda n, zeros everywhere else, and then you have this w matrix on the right, w11 through w1n, down through wn1 through wnn. And so if you think about how the matrix multiplication here works, row times column, it's still lambda 1 times w11. But if you think about like row times second column, it's now lambda 1 times w12. The lambda 1 agrees with the first coordinate of w here, whereas in this multiplication, the index of lambda agreed with the second index of w. On the right-hand side, you get the opposite. You get wij times lambda I. Okay. Now let's think what this is telling us. These guys are the same. This is the ith jth element in each matrix. So these need to be equal to each other. Well, if lambda I is distinct from lambda j, if lambda I is not equal to lambda j, if you have distinct eigenvalues, then it's like saying, well, if these guys are different, the only way for them to be equal is for your wij to be 0. Then wij is 0. So what that means is your W matrix, let me just recover some room over here. I think we can finish up this proof. Your W matrix would look like W11, W22, down through Wnn, and have zeros, everywhere else. Zeros everywhere else. Your W matrix is just a diagonal matrix. Of course, that may not be the case. You might have, for instance, that your lambda 1 equals your lambda 2. You could have repeated eigenvalues, right? So if you just think about the case where your W1 equals W2, your lambda 1 equals lambda 2, these guys will no longer be 0. Like if your lambda 1 equals lambda 2, you could have some non-zero guy here and some non-zero guy here. But you'll have little blocks. Well, you'll have a block of non-zero values that correspond to repeated eigenvalues. And so you can write W as some series of blocks. Some like block W1, some block W2, down through whatever the last block is, wk, that will correspond to clusters of eigenvalues that are the same, and zeros everywhere else. Where within D, you would have k clusters of eigenvalues that are the same. But then if you think about it, so here that is, if once you have this, now this just immediately follows, because W times the square root of D is just going to be equal to, well, this first block, you're just multiplying on the right by your first eigenvalue, which is all the same value, square root of your eigenvalue, which is all the same, and it's the same as multiplying by the left. So since each block, so these are going to be equal, since when you look at any block, if you just look at the block W1 times the matrix of eigenvalues that are all the same, lambda 1 through lambda 1, that's the same as lambda 1 through lambda 1 times W1. Right, this is exactly just scaling by the first eigenvalue. So all this does is you scale each block by the square root of your eigenvalues. Okay, so you can trace out the details of this a little bit more, but hopefully that gives you an idea of why this is true. What I really want to get to, though, is a really beautiful application of this. So trace out those details, but then you have, okay, any positive semi-definite matrix can be uniquely decomposed into some P, where P is a positive semi-definite matrix as well, decomposed into P squared. And so here is what I want to build up to. I'm going to state the theorem. It doesn't take much to prove. We actually have all the ingredients already. Well, I just erased a couple of them, but we have all the facts we need to prove it. But then I'm going to tell you what it means. And I mean, this is probably like one of your 100 best moments in undergraduate right now. So get ready for this. This is really quite fantastic. So here's the theorem. The theorem is called polar decomposition. And it states that given any matrix, complex values or real numbers, you can decide, we can write A is equal to UP, where U is a unitary matrix, P is your principal square root right there. So P is that principal square root, which you can think of as, if P squared is P star P, it's just the square root of that. It's you can define, well, one way to write this is just A star A square rooted. So if A was a PSD, a principal semi-definite matrix, that would recover this. But more generally, A is any matrix. So you can write A as if you do its conjugate transpose times itself, and then you take a square root. We'll show in a second that P is a nice PSD matrix that this gives you something analogous to there. So I'll show you that in a second, where this is unique. And this is unique if A happens to be invertible. Okay, so I guess I should just quickly, I'll at least prove existence. And then you can show uniqueness during an argument just like we did before. So A is not positive semi-definite. I'm not putting that restriction on A, right? So you just have some matrix A. And what I want to say is that although A is not positive semi-definite, when you multiply its conjugate transpose by itself, it is positive semi-definite. That was the theorem I just erased, right? to be positive semi-definite is equivalent to saying you can decompose this something conjugate transpose times itself. So this guy is positive semi-definite, right? And since it's positive semi-definite, it's going to have some root, some principal square root. And what is that principal square root? Well, it's just going to be this p. So we can check really fast. So, well, I mean, it's just defined to be the principal. It's just defined to be the square root, right? Like, then you know that A conjugate transpose A is equal to p squared for some positive semi-definite p. For some positive semi-definite p. So there you go. We just recovered, this is why this p always exists. But then I guess what you want to show is, okay, well if p is positive semi-definite, that means it's self-adjoint. So that means it's the same thing as p conjugate transpose times p. But now let's think what we just said. We have two different ways of decomposing some matrix. It's A conjugate transpose A and P conjugate transpose P. So what's the relationship between A and P? First thing we proved. Unitary freedom of a PS decomposition. Here I have two different PS decompositions, right? Here's some positive semi-definite matrix that's equal to decompose this way, decompose that way. Therefore, A and P must be equal up to a unitary matrix. Thus, A is just P up to some multiplication by a unitary matrix. So there's nothing new here. This is just a restatement of what we've already proven. You know, this just immediately follows from what we've already said. But like, this is beautiful. Like, you don't see it yet, but let me show you. Polar. Where does that word come from? Like, where have you seen that word before? Polar coordinates. So what is the story you learn, like, what is it, Calculus 2 or something, where you learn about polar coordinates? Okay. We're going to need lots of colors for this. So in calculus, you tell the story where you're like, oh, if I have some complex number hanging out here, call it z. You learn you can write z as what? What is polar coordinate way of writing z? Do you remember? Yeah, it's your distance, your radius, times the angle, where the angle is captured by e to the I theta, and your distance is captured by some r, right? So recall e to the I theta, that's just going to give you some, this guy here is just going to give you some location on the unit circle. Your angle, you know, if theta is pi over 4, whatever this is, it's going to pin down like that location right there. That's your e to the I theta. And then your r is a real number. So like it's this distance here, but really that r corresponds to some real number, right? And that real number is a non-negative real number, right? Like you could do this with negative, but you can just change the angle to make it always positive, right? It's usually one type of positive, non-negative radiuses. What this theorem says is the exact same thing is true for matrices. So instead of thinking of this as some point z, think of this as a point A, a matrix. And we said the matrix can be expressed as U times P. What is U? U is a unitary matrix. You should think of your unitary matrices as corresponding to your unit circle. Your unit circle is analogous to your family of unitary matrices. Right? I mean, unit circle are things with magnitude 1, right? And unitary matrices are those matrices whose vectors have norm 1. And the orthonormal, which means what are unitary matrices doing? Well, there's rotation matrices, or reflection. But it's like, unitary matrices are really just the guys rotating you around some unit circle. Or if you're in a higher dimensional space, like a unit sphere, right? But here's the two-dimensional picture. And then like, what is P? P is a positive semi-definite matrix. What's a positive semi-definite matrix? It's a matrix that has non-negative eigenvalues. And so you should think about your family of positive semi-definite matrices as corresponding to the non-negative portion of the real number line, right? Like all of these values where your x is greater than or equal to 0, this is analogous to your family of positive semi-definite matrices. But like the analogy is so much richer than this. So if you take the entire real number line, we would want to say that this entire real number line is analogous to the family of matrices that have eigenvalues that are either positive or negative, that have real eigenvalues. What are those? What do we call matrices that have real eigenvalues? What is it? Hermitian, self-adjoint, right? If you're Hermitian or self-adjoint, you have real eigenvalues. And how about, these are the matrices where A conjugate transpose equals A. And then how about like the imaginary line here? So that's the real number line. How about, what color haven't we used yet? Do I need a new color? Yellow. How about this imaginary? The line of imaginaries. Well, now we just want to think about matrices that have imaginary eigenvalues. And we haven't talked about it, but it's exactly analogous to how Hermitian has, I mean, you can probably figure it out. If Hermitian is real, then skew Hermitian are those matrices where A conjugate transpose is negative A. And like the analogy is even richer than this. It's like, what's the only non-negative number that lies on the unit circle? Non-negative real number that lies on a unit circle. What is that number right there? That's 1. That's 1. What is the only positive semi-definite matrix that's unitary? Well, it's identity matrix. How about right here? There's another, let me get another color. Well, we use red again for special points. What's the number that's right there? 0. Yeah, remember, this is not profound. What's the only matrix that's both Hermitian and skew Hermitian?
0.
Like if A conjugate transpose is A and it's minus A equals A, so it meets at 0. Right, like this is a really rich analogy. And so what polar decomposition is showing us is there's some really rich sense in which the matrices extend or generalize the structure they're used to from the complex numbers. May I also mention one more fact. You could write Z this way. You also are used to writing Z this way. You could also write Z as A plus BI, right? So what does it mean to write as A plus BI? It's some real number plus an imaginary number. So what would be the analogy for us? You could write A as what? Well, what are the things on this line down here? Hermitian matrices. A is equal to a Hermitian matrix plus, and then what are your like BI? What are the matrices over here? A skew Hermitian matrix. Turns out you can write A as a Hermitian plus a skew Hermitian matrix. So it's a really, really rich analogy that packs a lot of information into it that just, very deeply inspired by this polar decomposition. Okay, let's stop there.